When you first start your NDT journey, most of your theory training happens up front. But by the time you log all your on-the-job training hours and you're finally eligible to take the exam, that classroom knowledge isn't always fresh anymore. That's where the Liquid Penetrant Test Prep app comes in. With this app, you can keep your theory sharp while you build hands-on experience. It features 2 learning modes. Study mode gives you instant feedback and clear explanations for every question, helping you understand why each answer is correct. Test mode recreates the pressure of the real exam so you can strengthen your focus, speed, and confidence. Study anywhere, on breaks, in the field, or at home. The app tracks your performance automatically, showing you exactly where to focus next, so every minute of study moves you forward. Download the Liquid Penetrant Test Prep app today on the Apple App Store and take the next step toward a safer, stronger career in non-destructive testing.
Welcome back to the Deep Dive. This is where we take a deep, deep look into some really technical subjects and pull out the knowledge you need and usually some pretty cool facts along the way. Today, we are all in on a field where really a margin for error is 0. The stakes just couldn't be higher. We're talking about aerospace non-destructive testing.
That's right. And when we talk about flight safety, the inspection process isn't just rigorous. It's a completely different discipline than what you'd see in, say, general industry.
Yeah.
We're moving way beyond basic quality control and into mission-critical integrity.
Our focus today is aerospace applications of liquid penetrant testing. And for a lot of people, I think this method feels, basic. You dip a part, you look at it. But we're going to get into the intense rigor, the specialized, almost surgical chemistry, and some surprising research that's actually challenging decades of protocol.
All of it designed to keep something like a major rotating engine component from failing at 30,000 feet.
Our mission today is to really unpack that extreme regulatory environment, explore some truly exotic applications, like inspecting parts for liquid oxygen systems, and understand why, at the end of the day, human judgment, backed by intense training, is still the ultimate factor.
The decider on whether a part is truly flight-worthy.
Today's episode is brought to you by AMS Level 3. AMS Level 3 provides consulting, training, and compliance solutions to help companies build stronger, non-destructive testing programs. You can learn more about their services at the link in the video description. Okay, so let's unpack this. This is the crucial starting point. In general manufacturing, a liquid penetrant testing procedure, it might fit on one page.
Sure.
But in aerospace, that simple process is wrapped in this giant document, the process specification. Why does aerospace need this almost military-grade rulebook just to put die on a part?
Because in aerospace, what you're protecting against are these tiny, potentially catastrophic failure mechanisms, and they're highly dependent on environmental factors. So the process specification, it's the legal and the technical backbone.
It removes all the guesswork.
It removes all ambiguity. Make sure that every single time a part is inspected, whether it's a raw forging or during a final overhaul, the result is repeatable, traceable, and most importantly, reliable across the entire supply chain, no matter who does it.
So what are the core engineering requirements that these huge specifications actually address?
Yeah.
Because they aren't just suggestions, right? These are the pillars of compliance.
Exactly. Non-negotiable. The spec mandates 3 things for safe operation. First, it defines the precise procedures for applying the method.
Down to second.
Oh, yeah. We're talking time, temperature, pressure, every detail's locked down. Second, it defines the product acceptance classes. This is the engineering analysis that says this is an acceptable little surface feature versus this is a critical defect that needs to be rejected.
Okay. And the third?
And the third, which is arguably the most important, is the requirement for the qualification and control of both the equipment and, crucially, the personnel.
Right.
If any one of those 3 pillars is weak, the entire test is just invalid.
I get the feeling the specification isn't just a standalone document. It's more like a hub, right? It points to a whole library of other standards.
That's a great way to put it. It's a hub. A typical spec will list all the applicable external documents, military specs, consensus standards from groups like SAE, like EMS 2644.
Okay.
And then beyond the documents, it specifies material details, what type of penetrant, what sensitivity level, and it dictates requirements for every single step, the exact dwell time, the method for removing excess penetrant, and the inspection conditions, like the minimum UV light intensity in the booth.
The control over the materials themselves, that seems particularly fierce. So if I'm a manufacturer, I can't just buy the cheapest fluorescent penetrant on the market, even if it says high sensitivity, right on the can.
You absolutely cannot. No. This is where a standard like SAE AMS 2644 comes in, and specifically its Qualified Products List, or QPL. For any aerospace use, the materials must conform to and be qualified per that specific standard.
Yeah.
And they have to appear on that QPL. And this isn't just, bureaucratic nitpicking. It's a vital chemical control point.
So what's the risk you're trying to prevent with only using QPL materials? What could go wrong?
The primary risk, especially with the high-temperature alloys you see in turbines, is corrosion and material degradation. We are specifically trying to control contaminants, like high sulfur or high chlorine content. If a penetrant or developer has too much of that stuff, and the part is, say, a nickel-based superalloy operating under intense heat, that chemical residue can lead to catastrophic stress corrosion cracking later in service.
Wow.
So the QPL guarantees that the product's formulation has been chemically verified not to poison the flight material.
That makes the equipment requirements feel just as non-negotiable then. It's not just about having the tools. It's about having controlled tools. Can you give us an example of an equipment control that goes beyond just, common sense?
Yeah, let's take the drying process. After you clean a part or after you rinse off the penetrant, the part has to be dried.
Right.
If you use a heated dryer, it has to have active, verifiable temperature controls. But here's the detail. If you're using a hot air blast heater, the controls have to specifically ensure that the part surface temperature, not just the air temperature, does not exceed the maximum allowed.
And what's that limit, usually?
Typically around 70 degrees Celsius or 160 degrees Fahrenheit. And the reason is, if you get it too hot, you can literally damage or quench the fluorescent properties of the dye that's trapped in a crack.
So the defect becomes invisible.
It becomes invisible. The equipment is controlled to protect the chemistry.
It sounds like the entire system just requires this constant, redundant verification. The NDT lab is basically one continuous audit trail. You mentioned periodic checks and daily checks. What's the difference in focus there?
The separation is all about the rate of change. So periodic checks look at parameters that change slowly but fundamentally, often because of use or contamination over time. They ensure the long-term health of the system.
Okay.
Daily checks, on the other hand, are all about immediate operational integrity. It's what the inspector does right before their shift. Is the light working? Is the bath contaminated today?
So let's start with those periodic checks. What kind of tests are we talking about, and why are they so important for that long-term reliability?
They're critical. For water-washable penetrants, for instance, you have to periodically check the water content using a standard method like ASTM D95. Too much water, and the product's effectiveness just tanks.
Okay.
You also have to verify the penetrant sensitivity and its fluorescent brightness over time because the dye itself can break down. And of course, the obvious one. All the gauges for pressure and temperature and the crucial light meters for white light and UV radiation in the booth, they have to be calibrated periodically.
And the daily checks, that's like the inspector's pre-flight checklist.
Exactly. It's their ritual. Daily checks confirm the overall system performance. They check the penetrant and developer baths for any gross contamination. They check the condition of the dry developer. And the inspector absolutely must confirm the UV radiation intensity at the part surface and just verify the cleanliness of the whole area.
If that UV light is dim, you can't proceed.
You cannot proceed. It's a safety violation and a huge detection failure risk.
Let's focus on developer for a second. We've established it's required in most cases. What are some of the specific red flags for a developer that's, gone bad?
Well, developers, especially the aqueous or water-based types, are really sensitive to their composition. The specific gravity of an aqueous wet developer has to be checked at least weekly to make sure the concentration is right.
Too thick or too thin, and it doesn't work.
It won't draw the penetrant out correctly. And for both wet and dry developers, inspectors have to check for any unintended fluorescence every single day under a UV lamp.
What does that tell you? Unintended fluorescence.
It means it's contaminated. It means there's penetrant residue or oil or grease floating in the developer. And that could coat the surface of the next part and either cause false indications or, even worse, mask a real defect.
So you have to pause it.
Immediately. If unintended fluorescence is found, the material is rejected and replaced. No questions asked.
That attention to detail really reinforces how critical the material selection is. And the source makes it clear that material sensitivity isn't a one-size-fits-all choice. It's totally dependent on the application.
It is entirely governed by engineering needs. The process specification will dictate the sensitivity level you need based on how critical the component is and its surface finish. You have to think about the trade-off.
Which is what?
Higher sensitivity gives you greater detection reliability for sure, but it also increases the risk of finding non-relevant indications.
Like just surface roughness.
Exactly. Minor surface roughness that wastes a ton of time and complicates the whole inspection.
So you match the sensitivity to the risk. Give us those contrasting examples from the source material.
Okay, so if you're inspecting a raw forging where the surface is typically pretty rough and the discontinuities you're looking for are larger, a low sensitivity penetrant might be perfectly acceptable.
Right.
Using an ultra-high sensitivity product on that rough surface might just cause a mess of background fluorescence. But if you're inspecting a major rotating component like a compressor disc, something that's highly stressed, fracture critical, you must use an ultra-high sensitivity penetrant. That's SAE AMS 2644 level 4.
To find the tiniest crack.
To ensure that even the tiniest, tightest fatigue crack will be found. The sensitivity directly reflects the component's margin for error.
Which brings us to the human element. The source material really emphasizes that liquid penetrant testing, fundamentally it relies on the human eye and human judgment. So given that criticality, what are the requirements for the people doing the test?
This is the most crucial control point of all. Personnel have to be rigorously qualified according to industry standards like FNTTTC 1A and NAS 410. This means classroom instruction, documented on-the-job training, passing comprehensive exams.
And eye exams, I assume?
Strict visual acuity and cutter perception checks. Absolutely. If an inspector can't distinguish that fluorescent indication from the background, the test is useless.
And there's a key point here about who has the authority to disposition a part, who can look at an indication and say, that's a defect.
Yes, and this is where the Level 2 certification is the absolute linchpin. The specifications state clearly that personnel who read and interpret indications must be qualified to Level 2.
So that Level 2 technician, they have the final say right there on the floor. They don't need to call an engineer for every little thing.
That's right. They have the competence and knowledge to interpret the results, to look at a crack, measure it, compare it against the acceptance criteria, and make the final call. Accept, reject, or rework. The entire flow of production hinges on the competence of that Level 2 technician.
That person is a frontline safety officer with huge responsibility. So finally, let's talk about the written procedures. We talked about the big process specification, but the source notes that subcontractors have to prepare their own detailed written procedures for approval. Why the redundancy?
Well, the prime contractor gives them the overarching constitution, the process spec. But the subcontractor needs a bill of operation that's specific to their facility, their equipment, and the part's current stage.
Oh.
So they have to submit these procedures to the prime contractor's quality assurance team for approval. It guarantees traceability and uniformity.
And what has to be in that procedure?
Everything.
Yeah.
Everything has to be locked down. It needs to list the exact brand names and type designations of every material penetrant, cleaner, developer. It needs detailed descriptions of the cleaning and drying techniques with specific temperatures and times.
And the removal process.
Critically, it has to detail the precise removal techniques. If they're water rinsing, they have to specify the exact water pressure, usually around 275 kPa or 40 CI, and the temperature range. And, of course, the inspection standards, like dark adaptation time and minimum UV light levels. If they change a single brand of cleaner, they need reapproval.
Moving from the paper trail to the workshop floor, let's trace the actual steps. The first step, cleaning, seems obvious, but it's cited as the most frequent source of error.
It is the Achilles heel of liquid penetrant testing. If that part isn't perfectly clean, the test is just compromised from the start. You have to remove all contaminants, grease, oil, machining fluids, anything that could physically block the penetrant from getting into a crack.
What if the cleaning process itself is too aggressive, though?
That's the critical balance. Cleaning methods, which can sometimes include things like etching to remove surface smearing from machining, they have to be consistent with the contaminants, but fundamentally, they must not be detrimental to the component itself.
You can't damage the part you're trying to save.
Exactly. You can't compromise the structural integrity just to clean the surface.
Okay, so once it's clean, penetrant application and dwell time, what's the standard environment for this part of the process?
For fluorescent liquid penetrant testing, or Type 1, both the part and the penetrant have to be kept within a specific temperature range, usually about 4 to 49 degrees Celsius. That's 40 to 120 Fahrenheit. Application is usually just spraying, dipping, or brushing.
And the timing is critical. What are the minimum and maximum dwell times?
The minimum dwell time, that's the time the penetrant soaks into the crack, is typically 10 minutes, but it can be longer depending on the part. And the maximum dwell time is just as important. If you go over 2 hours, the penetrant can start to dry on the surface, which really messes with the removal step.
So you have to start over.
You have to clean it and start all over again.
Now, for the removal of the excess penetrant, you've mentioned this is a really high-stakes step, especially for water-washable penetrants.
This is the most delicate phase. It's often called the controlled wash. And the big danger here is overwashing. It is the most common operator mistake.
So that's the big one, right? The mistake everyone's warned about.
Oh, absolutely. Overwashing. If you're using a manual spray, the water pressure is strictly limited to prevent it from physically eroding the penetrant that's sitting inside the crack.
And what is that pressure limit? And what happens if you go over it?
The pressure can't exceed 275 kPa, which is about 40 pounds a gallon managed to. If you exceed that, or you just spray for too long, you're overwashing. And you literally wash the penetrant out of the discontinuity.
You're washing away the evidence.
Exactly. The indication disappears. And if an inspector suspects overwashing has happened, the component has to be completely cleaned, dried, and reprocessed from the very beginning.
Wow. The cost of reprocessing a major engine component due to that must be immense.
It's massive. And it just emphasizes the need for training. After the rinse, we move to drying. Again, temperature control is paramount. The oven can't exceed 70 degrees Celsius or 160 Fahrenheit. And the drying time should only be as long as necessary. Too much heat or too much time can damage the fluorescence.
Okay, next up, the developer. We know it's generally required, but are there ever scenarios in aerospace where you can actually waive the use of a developer?
Yes, but only with proper justification and, of course, approval. The source points out that for fluorescent testing, developers can sometimes be waived during the manufacturing inspection of, say, Class 3 or Class 4 castings. These are non-critical structures, but it needs explicit approval from the contracting agency. Otherwise, it's considered necessary.
Let's talk about the common types. What are the specific requirements for non-aqueous wet developers, the ones that usually come in a spray can?
Non-aqueous wet developers have to be applied as a uniform, thin coating. The key word there is thin. If the coating is too thick, the developer itself can actually mask the indications. It creates this dense layer that the faint fluorescence can't shine through. And if that happens,
Back to square one.
clean and reprocess. The development time is also tightly controlled. A minimum of 10 minutes, but a maximum of 60 usually.
Once the developer's done its job, the inspector moves to the booth. And the inspection environment itself is regulated to a precise degree. Tell us about the light requirements.
The inspection for fluorescent PT has to happen in a severely darkened booth. The ambient white light has to be less than 20 lux. That is incredibly dark.
Like a full moon.
Just a little more light than a full moon on a clear night. It's all about maximizing the contrast.
And the inspector has to prep their eyes for this darkness.
Correct. The inspector needs a minimum of 1 minute for dark adaptation before they even start the test. This lets the rods in their eyes get sensitive enough to reliably see those faint indications.
And the UV light intensity, what's the minimum there, and why is that number so strict?
The ultraviolet radiation intensity at the port surface is crucial. The lamp has to warm up for at least 5 minutes, and the intensity must be a minimum of 10 WAM2, which is 1000 WAM2. If that light is too dim, the indications just won't fluoresce brightly enough to be seen, especially for very small cracks. It's a safety factor.
So after all that prep and process control, the level 2 technician is looking at the indications. How are they dispositioned? This is where structural engineering meets NDT.
The criteria are defined based on the stress analysis of that part. Indications get classified into 2 broad categories, linear and rounded. And linear indications are the most worrisome. They often suggest a crack or a lap or a tear or something that's going to propagate under stress.
What's the rejection rule for a linear indication?
It's simple and it's strict. Any indication is unacceptable if its length is more than 3 times its width. If it's longer than 3 to 1, it's rejected. Period.
And rounded indications, things like porosity, they have a much more complex set of criteria, right? Dealing with how close they are to each other.
That's right. Rounded indications are governed by rules about their density in a certain area and their separation distance. That's the key for structural integrity.
Tell us about that separation rule.
If you have 2 adjacent rounded indications, they have to be separated by a distance of at least 4 times the diameter of the larger one.
Why so specific?
Because if they're too close, they're considered to be coalescing under stress. They start to act like a single, larger, and potentially linear defect. So if you have 4 more rounded indications that are lined up, and they violate that separation rule, the part is typically rejected. It prevents multiple small defects from forming a critical stress riser.
Okay, so this next part is fascinating because it seems to challenge something that's, almost sacred in liquid penetrant testing, the mandatory use of a developer.
Yeah, this is where the story gets really interesting because the industry went through this sort of sensitivity evolution. For decades, the gold standard for critical parts was post-emulsified penetrants. They were great for sensitivity. But as components got larger, the time required to emulsify the penetrant consistently across those huge surfaces became a real problem. It often led to reduced sensitivity.
So manufacturers developed new water-washable penetrants that performed better on big parts. But then the definition of sensitivity changed, and that caused a conflict.
Exactly. The Department of Defense modified its classification approach, and the new metric they used to define ultra-high sensitivity was based on the brightness of developer-enhanced indications on tiny fatigue cracks. And suddenly, these new water-washable penetrants, which performed great in the field, they failed the new standard if you omitted the developer step.
So the big question became, is the developer actually helping you find a crack that was invisible before, or is it just making a crack you could already see much, much brighter?
Precisely. Is it enhancing detectability or just visibility? This prompted a huge collaborative study with the Aerospace Industries Association and the Air Force Research Lab. Their goal was to see if, for certain applications, developers were truly necessary.
So how did they even test this? How do you create a perfect, tiny, repeatable crack for a study like this?
It was ingenious. They started with these extruded aluminum blanks, and they machined V-grooves into them. Then they put electric discharge machined, or EDM notches, at the bottom of the grooves.
Okay.
Then, and this is the key step, they compressed the blanks. That compression process basically closed up those machine notches, simulating the kind of surface smearing and tightness you find in real-world manufacturing.
So they were mimicking the mechanical closure of a real crack.
Yes. Finally, they just milled away the grooves, leaving a smooth surface with the remnants of these compressed cracks underneath. And this created extremely tight discontinuities, some with surface openings as narrow as 2.5 micrometer.
That's microscopic. So they run the experiment, inspect without developer first, then immediately inspect again with dry developer. What were the overall results?
The efficiency was very high across all the companies,
right.
98% detection rate. But the core finding, the comparison of with versus without developer, that was the big surprise.
What was it?
It was the major takeaway that challenged decades of NDT tradition. In all cases, discontinuities that were detected with the application of developer were also detected without the developer.
Wow. So, just to be clear, every single flaw they found with developer, they also found without it.
Every single one. Across every test location. It showed that if a good water-washable penetrant could get into the crack, the developer was just acting as an intensifier. But it wasn't necessary for the initial detection of these specific manufacturing flaws.
It makes it easier to see, but it doesn't make it visible in the first place.
Exactly. The developer drastically enhanced the brilliance and the contrast, but it didn't change whether the crack was found or not.
So if you're going to remove the developer, how do you compensate for that loss of brilliance to make sure your detection reliability stays up at that 98%?
That's where the recommended operational change came in. To ensure reliable detection without the developer, the study recommended significantly increasing the ultraviolet radiation intensity at the part surface. They proposed boosting the minimum required intensity from the standard 10 WM2 up to 30 WM2, so 3000 WC-2. Basically, they compensated for the lack of chemical enhancement by just blasting it with light energy.
That is a massive amount of light. So what are the implications here? Does this mean the aerospace industry can just ditch developer entirely?
Not at all, no. It means that liquid penetrant testing without developer might be appropriate for detecting manufacturing discontinuities in non-fracture critical aluminum parts with the right engineering approval.
So what's the fundamental caveat? What keeps developer mandatory for the most critical parts?
The crucial caveat is the difference between a manufacturing discontinuity and a true fatigue crack. The flaws in the study were tight, but they weren't fatigue cracks. Fatigue cracks are inherently much tighter, often invisible until they're microns deep, and they have a much smaller internal reservoir to hold the penetrant.
So for the highest stakes components, you still need that chemical pump, the developer, to guarantee the indication is visible. That distinction is key.
For a fracture-critical part, the tiny amount of penetrant in that crack often requires the developer's wicking action to actively draw it out and make it bright enough to see reliably. That's the difference.
We also like to recognize Skaggs Media LLC as the creative force behind today's podcasts. Skaggs Media specializes in helping businesses build a strong presence on social media through strategy, content, and storytelling that connects. Find out more at skaggsmedia.com.
All right, let's talk about some really extreme environments. What happens when you need to inspect a part that's going to be in contact with liquid oxygen?
We shift now from general compliance to true extremes. When a component is designed to interact with liquid oxygen systems, valves, pumps, cryogenic tanks, the standard rules of liquid penetrant testing inspection become completely insufficient.
Why is liquid oxygen, or LOX, so uniquely hazardous in this context?
LOX is an extremely powerful oxidizer. Any organic residue, and that includes the oil or dye from standard penetrant materials, can react violently with the LOX under impact or shock.
We're talking about an explosion, a potential catastrophic detonation. So the inspection process itself must be guaranteed not to introduce a detonation hazard.
So the whole system, the penetrant, the cleaner, everything has to be LOX compatible while still finding the cracks. What are the two main safety approaches they developed for this?
The first approach is to design systems where all the elements are highly volatile and they just dissipate by evaporation. These are the so-called self-destruct penetrants. But the preferred approach is actually to use materials that are inherently water-soluble because they can be completely removed during post-cleaning.
And why is water solubility safer than just letting it evaporate?
Because water-soluble materials can be flushed and diluted almost infinitely. The residue dissolves easily, and the cleaning agent itself, which is just water, can be fully rinsed away. It's much easier to guarantee complete removal.
So what are the challenges with those self-destruct systems then?
The major hurdle is the fluorescent dye itself. Most organic fluorescent dyes are chemically reactive with LOX, so to make a volatile system work, you need these specialized dyes, often from the coumarine chemical class, that sublime or dissipate quickly at relatively low heat.
And if you heat the part to speed it up?
You can, but that introduces a new concern. Redeposition. Will that trace amount of dye, when it vaporizes, just redeposit somewhere else that's hard to clean? You need absolute certainty that dissipation means 100% removal, which is incredibly hard to guarantee.
Given these risks, there must be an extreme test to certify these materials. Tell us about the LOX impact test.
The LOX impact test is the ultimate gatekeeper. It's a severe mechanical test designed to simulate a massive shock. A typical test involves dropping a heavy plummet, about 9 kilograms from a meter high, right onto the test substance.
And they do this how many times?
20 times, to ensure reliability. And the material is instantly rejected if there's any evidence of a reaction, an audible explosion, a visible flash, any discoloration or charring. It has to be completely inert under severe mechanical stress.
That's incredible rigor. Now let's pivot to another chemical application that sounds like it's straight out of a sci-fi movie. Using liquid penetrant testing to determine not just if a crack is there, but how deep it is.
This is a truly innovative application, especially for composite aircraft structures. A lot of composite skins are layered over a metallic substrate, like an aluminum honeycomb core.
Right.
If moisture or a crack gets to the composite down to that metal, you get catastrophic corrosion. So you need a way to detect the exact moment a crack hits the metal.
And the mechanism relies on adding a chelating agent to the penetrant. Simplify what a chelating agent does for us.
Think of the chelating agent as a specialized chemical handshake. A chelating agent, like 8-hydroxyquinoline, is added to a very low surface tension carrier, usually isopropyl alcohol. And the key is that this agent has a chemical affinity for metallic ions, aluminum, iron, copper.
And when that handshake happens?
When the chemical complex forms, when the agent binds to the metal ion, it fundamentally shifts its fluorescence spectrum. The original penetrant fluoresces in the UV range. But once it touches the metal, it shifts to a longer wavelength, an easily detected color in the visible spectrum.
So it changes color when it touches metal. That's the signal.
Precisely. The inspector sees the regular fluorescent indication, but if it suddenly glows a different secondary color, they know immediately that the discontinuity has reached that vulnerable aluminum core.
This sounds like it has some major advantages beyond just the depth sensing.
It does. First, the carrier, being low surface tension like alcohol, it penetrates small cracks much faster than water or oil-based penetrants. Second, the system is relatively inexpensive. And critically for maintenance, it avoids oil contamination, which is a huge problem for composite repair procedures.
Let's look at another hyper-specific, really challenging inspection. The brazed joints in open-face honeycomb seals in gas turbines. Why can't you just use X-ray or ultrasound on this part?
The geometry just defeats conventional NDT. The honeycomb is open at the inner diameter, and it's brazed to a solid ring at the outer diameter. It's basically a ring of tiny individual cells, and you need to check the braze at the bottom of each one. X-ray doesn't have the resolution, and ultrasound struggles with the air-filled cells.
So they came up with a specialized liquid penetrant derivative that uses these extremely low viscosity liquids. How does that liquid reveal a braze defect?
They're leveraging the fundamental physics of capillary action and surface tension. So the ring is immersed in the liquid, allowed to dwell, and then it's removed and rotated about 30 degrees while being inspected under bright white light.
And what's the visual cue? What signals a good braze versus a failed one?
If a cell has a good, intact braze joint, the high surface tension forces create a meniscus across the top of the cell, holding the liquid inside. It basically seals it. But if the braze is poor, the liquid drains out due to the slight force from the rotation. This drainage creates a visible shadow area inside the cell. That's your defect.
And to make this more reliable, they add a fluorescent tracer.
Yes, because the white light contrast can be subtle. By adding a supersensitive fluorescent tracer, the contrast is amplified significantly. Under UV light, the good liquid-filled cells look distinctly blue. The unbrazed or leaking cells, now empty, they look dark or have a greenish tint. It makes the defect unambiguous.
So the rotation is literally just increasing the force of gravity on the liquid enough to overcome the capillary action of a bad cell, but not enough to break the surface tension seal of a good one.
That's the physics behind it. But there is a limitation. If the cell is very deep and narrow a height-to-width ratio above 3:1, the surface tension can be so dominant that it might prevent the liquid from flowing out of an unbrazed cell, so the operator has to understand those geometric limits.
Moving to another challenge, high-precision weldments and investment castings. These can develop extremely tight microcracks that conventional liquid penetrant testing just misses. Why are they missed?
Two reasons. First, the cracks are so narrow that the amount of penetrant that bleeds back out is often insufficient to overcome the thin film fluorescence threshold. It's just too faint to see.
Okay.
And second, a lot of parts coming from service have contaminants, oxides, acids trapped in the crack that physically repel the penetrant even after cleaning.
So just letting it sit there, the static dwell, isn't aggressive enough to get in. The solution in the source is to use ultrasonic pumping.
Correct. This technique uses ultrasound at an optimized frequency to actively pump the fluorescent penetrant into the tightest discontinuities. It turns a passive soak into an active, energized filling process.
And what are the benefits of using that ultrasonic energy?
It provides three major advantages almost at the same time. First, the ultrasound physically helps shake loose and flush out those trapped contaminants. Second, it flushes the interfaces clean. And third, and most importantly, it rapidly deposits the fluid deep into the crack, which minimizes the required dwell time. You're force-feeding the penetrant into the defect.
So you're going from, what, hours to just a few minutes?
The time reduction is staggering. The total time from the start of cleaning to being ready to inspect can be reduced to 5 minutes or less. We're talking 30 seconds of ultrasonic cleaning, 60 seconds of drying, and then maybe 30 seconds of ultrasonic penetrant application.
And I imagine the frequency of that ultrasound has to be carefully controlled, or you could damage the part you're trying to inspect.
Yes, frequency is critical. It depends on the part's geometry and fragility. Lower frequencies have more power, so they're better for massive parts, but they can be noisy and potentially damaging to delicate components. So inspectors have to select the highest frequency that still provides adequate penetration for the crack size they're looking for.
Let's shift our focus to the maintenance side of the commercial airline industry. Liquid penetrant testing is absolutely critical during the base overhaul phase, which is all about prevention.
Routine maintenance is where NDT saves billions of dollars. Base overhauls happen at extended intervals, maybe between 2,000 and 5,000 flight hours. And at this stage, liquid penetrant testing is essential for detecting fatigue cracks in their incipient state.
When they're just starting.
Just beginning. Finding and repairing these cracks early prevents catastrophic failure, and it avoids unscheduled service disruption, which is the single biggest cost for airlines.
But maintenance environments have a major complication that you don't really find in manufacturing: the extensive use of sealants?
Sealants are a huge inspection headache. They're applied everywhere, for fuel containment in the wings, cabin pressure, and even a thin film of it can severely compromise the test.
How does the sealant interfere?
It creates a double risk. First, it can vaguely bridge over a structural crack in the metal, preventing the penetrant from even getting in. The crack is there, but the inspection is blind.
And the second risk.
Second, cracks or voids in the sealant itself can trap penetrant and create false indications that look just like a structural defect. This can lead to unnecessary disassembly and repair. The inspector is constantly trying to distinguish between a defect in the metal and a defect in the sealant.
And what about field or line testing, where inspectors are doing quick checks without a clean, dedicated hanger?
Field testing, which is common for military repair units, severely limits the available methods. Fluorescent liquid penetrant testing is a real challenge because the inspector has to completely mask or shield the area from white light to get that required darkness, which is cumbersome and sometimes hazardous when you're working up on scaffolding.
And if they try to switch between fluorescent and visible dye penetrants, they face a serious contamination risk.
A very serious risk. If a visible dye penetrant was used first, there's no guarantee all of it was removed. And if any of that visible dye residue remains, it will quench the fluorescence of the next penetrant, rendering the reinspection useless.
Let's turn now to the highest stress, most exotic applications possible. Components for deep space probes, like the radioisotope heat source capsules. These parts operate at over 1100 degrees Celsius and are made of fragile, exotic alloys.
These are often highly engineered alloys, tantalum, platinum, with extremely tight tolerances. They're fragile, so handling must be minimized to prevent damage and contamination. And liquid penetrant testing is mandatory, but the challenge is reducing those handling steps.
And the solution was radical, eliminating the developer step entirely, but with a unique approach.
Exactly. The developer application and removal were identified as the steps with the greatest risk of damage. So to mitigate this, they adopted a proprietary, water-washable, self-developing fluorescent liquid penetrant system. This effectively eliminated 2 handling steps from the process.
But if these are such critical parts, how did they ensure they had enough sensitivity without the developer's enhancing effect?
They used a technique called sensitivity tuning. Instead of using a single off-the-shelf product, they mixed a family of compatible penetrants, an ultra-high sensitivity component with a lower sensitivity one. And by controlling that ratio, they could achieve a custom intermediate sensitivity, like a 2.5.
Why customize it? Why not just use the highest available sensitivity?
Because the goal isn't just to find the tiniest possible crack, it's to maximize detection reliability without getting an excessive number of non-relevant indications. The forming processes for these exotic alloys often create surface features that a level 4 penetrant would flag, but that are structurally irrelevant. Tuning this sensitivity lets them find the critical flaws while minimizing the false positives.
That is an incredible level of control. Another example cited was inspecting stainless steel welds for the LOFT reactor fuel modules. Why developer list there?
The LOFT reactor was highly instrumented. The challenge was that applying developer spray would contaminate the incredibly intricate areas between the instrumentation leads. It would have been a nightmare to clean. So by using a high-sensitivity fluorescent liquid penetrant without developer, they solved the contamination problem while maintaining detection capability.
And just like in the aluminum study, they had to compensate for the missing developer.
Correct. They implemented the same strategy.
Yeah.
Boosting the ultraviolet radiation intensity from the standard minimum of 10 WM2 up to a much higher minimum of 30 WM2. That increased illumination provided the visual enhancement that the developer would have.
Finally, let's discuss the Advanced Test Reactor, or ATR, fuel elements. The rejection criteria for these components, which operate under immense heat and radiation, are some of the strictest in the entire NDT world.
They reflect a zero-tolerance policy. For the ATR fuel elements, the criteria are absolute. There must be no linear discontinuities whatsoever. A linear indication suggests a crack pathway, which is immediately unacceptable.
And the criteria for rounded indications are also incredibly tight.
They are. Rejection occurs if you have 4 or more rounded indications that are lined up and are separated by 1.6 millimeters or less. Any clustering that suggests a potential stress point is rejected.
And the process specification also tightly restricts what you can do to the surface before inspection. Why is that restriction so crucial?
Because surface treatments can mask a defect. The specifications strictly forbid any process that might smear the surface opening or bridge over a discontinuity before the test. This includes plating, anodizing, painting, or any kind of peening action like shot blasting. The part has to be inspected in its true structural condition.
This entire deep dive has really shown that in aerospace, nuclear, and deep space applications, liquid penetrant testing is so far from a simple process. It's a dynamic, specialized field where the rulebook is constantly rewritten and tuned for every single unique component.
It's the ultimate testament to risk mitigation. The rigorous control of materials, the extreme qualification of personnel, and the willingness to challenge established procedures, like the finding that developer may not be necessary for certain flaws, it all reflects the constant evolutionary nature of safety.
Right.
The integrity required for a platinum alloy capsule going to deep space fundamentally raises the safety bar for every single item that flies. NDT compliance is a living, breathing defense system against failure.
The ultimate knowledge nugget we can leave you with is this. The ability to detect a 2.5 micrometer crack or to chemically determine if a fracture has reached a metal core is what separates functional engineering from catastrophic failure. And the standards learned in these extreme fields, they filter down and ultimately make every component safer and more reliable. Before we wrap up, a quick reminder that AMS Level 3 is here to support your non-destructive testing needs, whether it's Level 3 consulting, training and mentorship, or compliance solutions like NADCAP and FAA readiness. To learn more, visit amsl3.com. And don't forget to follow our YouTube channel for more insights and updates on non-destructive testing. Thank you for joining us on this deep dive into the intense world of aerospace liquid penetrant testing. We'll see you next time.
When you first start your NDT journey, most of your theory training happens up front. But by the time you log all your on-the-job training hours and you're finally eligible to take the exam, that classroom knowledge isn't always fresh anymore. That's where the Liquid Penetrant Test Prep app comes in. With this app, you can keep your theory sharp while you build hands-on experience. It features 2 learning modes. Study mode gives you instant feedback and clear explanations for every question, helping you understand why each answer is correct. Test mode recreates the pressure of the real exam so you can strengthen your focus, speed, and confidence. Study anywhere, on breaks, in the field, or at home. The app tracks your performance automatically, showing you exactly where to focus next, so every minute of study moves you forward. Download the Liquid Penetrant Test Prep app today on the Apple App Store and take the next step toward a safer, stronger career in non-destructive testing.